everybody. I hope everyone's having a wonderful day. So we're going to get started with the next topic. It's part of an introduction. It will be algorithms. So I've so far talked about what data structures are, talked about what a problem is, that problems have input sizes. So remember, you can think of the input size as the number of items for which you encode your input in, where each one of the numbers, like say if I give you an array, you can think of each one of the numbers as some encoding of a fixed number of bits that your computer would be able to read. Okay? We're going to keep it kind of simple like that. So what we're going to do is I'm going to kind of put everything together. So I have to give us a working definition of an algorithm. Now there's several different algorithm definitions you might encounter. Some are more formal than others. This one will do mostly fine in an undergraduate level computer science class. There is a more formal definition, but that's beyond the scope of this course. But this one is pretty much a working definition that most algorithms researchers use. So it's a pretty good definition. So an algorithm, I'm going to read it with you because this definition is very important. It is an unambiguous step-by-step procedure that takes an input instance of a given problem as input and produces output for the problem instance. So you'll notice that our definition here is tied intimately around problems. So you're going to imagine it like I have some problem, I pluck off one of those problem instances, I feed its inputs to the inputs of my algorithm, and then the algorithm solves that problem. Then we ask the question of if it's correct or not, right? I produce some output, and we say that the output of an algorithm is called correct if it is the solution to the problem instance. So in our example with the sorting problem, remember I gave you some array with some numbers in it, and I want to ask, hey look, if I have a bunch of numbers, the solution is that sorted in non-decreasing order from smallest to largest. So you got to look at this as if I gave you an algorithm and it correctly outputted that sorted order, then we say the output is correct, okay? So I want to give you a picture. I like drawing this picture for students because I find it really helps put everything together that we've been talking about. So I find this is a pretty helpful picture. Because there's a lot of terminology kicking around. I just really want to cut down to the middle of everything. So imagine I give you a problem instance. So remember, this is one of those dots in my circle where the circle represents all of my instances. And each one, remember, is some input, and that input is encoded with some number of bits. And that number of bits, that's our input size, okay? So usually we refer to the problem instance as inputs, specifically as the input instance or as inputs. In fact, you'll find very often that people will use this phrase and that phrase synonymously with the word instance, like I said the other day. So an input instance, like I said, has input, which I'll just refer to as input instance, and it has a solution. Likewise, I have this other definition I just gave you of an algorithm. So I have an algorithm. So I have this notion of an algorithm. The algorithm has inputs. So these would be your parameters that accept inputs, and it has output. So how exactly does this algorithm, what did we say in this definition? We say that it takes an input and produces output. So what does the algorithm do? Well, it takes an input, it will produce some output, right? But to do that, I have to be able to do something, right? I have to give some input instance as input, right? So I give this to the algorithm, and it gets given as input. That input gets processed by the algorithm using this step-by-step procedure to produce output. And then finally, we just do one last thing to determine if it's correct or not. We check if it's we don't know if it's correct or not. We don't know if this is correct. Now, remember, I told you that the problem instance doesn't, it's really just this input. I'm just associating with its solution to make it easier to understand. So, that being said, you can't literally just be given this and the solution as part of the input of the algorithm. It's only the inputs, those parameters that have been assigned values. So, we don't necessarily know all the time if our algorithm produces correct output, which I'll get to in a moment. So this is kind of like the picture I want you to have in your head. So I take inputs from the problem instance, I feed it as input to the algorithm processes that, produces output. And then we just simply want to know if this is correct or incorrect. Okay? Now, there's a few things I want to highlight about our definition of an algorithm. The first thing is that it's unambiguous, and that means that if I give you an algorithm, there's no way you can twist, you can mangle what I've said. It has to be precise in such a way that it's exact, meaning that if there isn't going to be some way that you couldn't follow my algorithm and get the wrong answer if indeed my algorithm were correct. Likewise, you want to think of unambiguous in a contextual way, because you might ask, okay, well, how do you know if you're following the person's algorithm correctly? Now, algorithms are often given in various forms. In words, like in English, you'll find very often I do this. You'll find I'll use pseudocode. So this is a machine-independent, programming code that doesn't really have any one solid convention to it. But you'll find that I'll follow a consistent set of rules to write down what it should look like. So it could look like words, but the words have to be unambiguous to the reader. So it means that when I say unambiguous, it has to be clear enough for your audience. So that's what I mean by contextual. So if I'm writing an algorithm up to a bunch of algorithms experts, they won't be very particular or picky about me skipping a couple of steps here or there, because they will be aware of the things I describe. So I might describe a name of an algorithm. They will know what that algorithm is, or I may even just say, solve this problem, and I'll give the name of the problem. They will know what that problem is, and they'll know about algorithms for that problem. However, at the level for which you're introducing an algorithm, you want to avoid doing things like this. You want to be as clear as possible without any ambiguity. Some way that somebody can take what you've written and twist it such that it doesn't make a whole lot of sense to them. So you got to be not overly charitable with your audience. That's basically what I'm saying. Likewise, it is step by step. That means that each operation that you perform, there isn't a way you can split the operations into multiple ones that are occurring all at the exact same time. Every operation has to precede a previously stated operation. It's so-called deterministic. Now, this is in contrast to some other types of processes you may encounter in future studies, say, for example, parallel algorithms. Parallel algorithms, they do operate in a way that I described, sort of, but not entirely, because technically still, each one is being operated on in parallel by different machines. Here, my definition still applies because I'm assuming there's just one computer, okay? We'll talk more about what that means later. So, this is what we're going to consider an algorithm. So, where exactly are we going to go with this? So, the big idea here is that you might know some algorithms already. So, I'm going to say you may, for example, be aware of some algorithms for sorting. So remember I gave you a sorting problem last day? So you may be aware of some algorithms for sorting. Think about some algorithms for sorting. So if I give you an array, I want to know how you can sort it. So I give you an array, you return back the sorted array. So I want you to think about that while I'm erasing this. Okay. So let's think about some examples. So I'm just going to rattle off a fun list of these, okay? So Okay, let's just think of the first kind of one you could think of as like bubble sort. There's bubble sort. You may know of insertion sort. What are some other ones? How about selection sort? Selection sort's another sorting algorithm. How about, let's go into the beefier boys. The beefier guys. Quicksort. Quicksort is a rather interesting sorting algorithm. How about heap sort? Heap sort is interesting. How about merge sort? Merge sort is another sorting algorithm. So each of these algorithms would fit within this framework if I gave you my sorting problem. So each one of these I get an array. I can give it, let's say, for example, bubble sort. And bubble sort will take those inputs, it'll produce as output a sorted array. And it, in fact, is the correct algorithm, which I'm going to define in a moment. So all of these are algorithms for the sorting problem I defined. So I'm going to say each problem, we'll say each algorithm. So each algorithm above solves our sorting problem. Not one of these algorithms will produce incorrect output for one instance. That means I give you an array, it will sort it. There won't be just like one instance that bubble sort just can't handle and it'll just not sort it correctly. So computer scientists strive for algorithms that follow this type of setup, where I have an algorithm, it always will produce the correct output. That is the goal very much when you talk about designing classically algorithms. So that's generally that's kind of like the gold mark, is getting an algorithm that is correct. So that's what we're going to talk about. An algorithm is correct. Now you might guess what I mean by this. If for every instance of a problem given, the algorithm always produces correct output. So that's what our definition of what a correct algorithm is. So there's no fudging around with the way our input works. Now, to show an algorithm is correct, we need to prove a couple of things. So remember, I said that the algorithm is some finite step-by-step procedure, right? So there's one requirement in that way of phrasing things, right? Is that the algorithm actually has to be able to terminate. Because clearly it has to do the process when it spits out the output for me, right? So that's going to be one requirement we're going to need for correctness, because obviously there's no, well, I try to avoid the word obviously, but it should be obvious that I can't produce output if the algorithm just keeps running on forever, right? So to show an algorithm is correct, we will prove so we have two things we're going to prove. That the algorithm terminates terminates in finite time. So this is a termination condition. So this is termination. So we're going to prove that the algorithm actually terminates. In very realistic terms, imagine if I were to implement an algorithm on a computer. What you'd want to have is this condition, so you make sure that the program actually stops. we need to have this in place. Likewise, the algorithm produces correct output. So this is our condition of having correct output. So if you prove these two things, the algorithm must be correct because it terminates, so it means it produces output, and we're going to prove that the algorithm in fact produces correct output, no matter what input instance you give. Now, this brings me to an important point I need to make, is if I give you some problem and you attempt to propose an algorithm for it, you need to be very particular and careful about this kind of claim. Because you can't just simply run a bunch of tests on an algorithm when you implement it to certify that the algorithm is in fact correct. You'll notice in our definition and framework, that isn't a thing because you can't possibly, unless you're really a whiz with symbolic computation, and that only works in very specific circumstances, where you're going to have it where you can actually say, hey, look, I can check an infinite number of problem instances. That, unfortunately, we can't really do that, right? I can check problem instance 1, problem instance 2, problem instance 3. I sample a whole bunch, like say 100,000 instances. And I'm trying to be very serious about this. Is I have 100,000 instances. You do the experiment and you check, okay, is it working? And you find, yeah, it works perfectly fine. Look, thumbs up. I think we're all good to go. Now, that is you projecting your assumption that it is pretty okay. But that, on a more mathematical level, the dreaded M word, the mayonnaise, dreaded M word, you have to be a bit more particular and careful, because that might be good enough for you, but the standard for which algorithms are defined and how we define correctness in computer science is that it has to be correct always. So you can't just simply sample 100,000 and say, hey, look, it's all good to go. Because there's a very real possibility that now you could trust yourself, you might trust your friend, but there might be somebody out there that might be like, okay, well, I don't know, I'll just pick 100,000 instances. I'll just avoid the ones that maybe cause problems for my algorithm, and I'll publish this in somewhere, and I'll just say, this is good enough. That is something you have to be very wary of. Because they may have picked the wrong problem instance for which that algorithm actually does not work correctly. So you have to be very careful about what the claims are being made about the algorithm in question. But if it has to be correct, it has to be correct for every problem instance. That's the point. If you ran 100,000 experiments and you just check, hey, look, is it working? And you find it works. That might be a good likely chance that it might be correct. However, there might be a 100,001st instance that is actually incorrect that you just didn't check. Okay? So that's just my point I need to make about that. So you cannot just create just a simple little test program and just check your algorithm and see if it works. Usually in those kind of cases where you're doing debugging, you would identify test candidates or benchmarks just to see how well it's going. But the claim of correctness is something that's a much stronger claim than just that. Okay? So, to give an example of this, I'm going to consider a type of search problem. Remember, I talked about search problems last day. Remember, I gave you a set S and some key X. And I just want to know if X is in S. So I'm going to revisit the search problem here, but I'm going to do it within a more traditional landscape. So here's an example. So I'm going to consider So again, we're going to talk about the search problem. Here's the search problem. So I'm just going to say for simplicity, we assume here that S is a set of n integers stored in we'll just store it in a we'll go with this. Let's go with this. In non-decreasing order. In an array L. Okay, so I've made a very particular assumption here that the set S is stored in an array, but the array is actually it's technically sorted already. It's sorted from smallest to largest. Now, you can't normally just make this kind of assumption when you're searching in an array L. This is a particular kind of search problem. So you can think of this as a particular search problem. So this is a particular search problem. Now, you might know of a couple ways you can tackle trying to do a search in this. So I want to do the following. I want to find X. I want to find the position of X because L is an array, right? And L has positions in it. By convention, I'm just going to assume that -1 means that it's not in L. But before anything, we have to talk about input size. So remember, we need to consider the input size of a problem like this. So remember, the input size is an array with n integers in it. So what's the input size here? Well, I have n integers. Just think of each one of these integers being some fixed number of bits. Well, let's think about that. Well, it's just the size of the array, which is just n, right? So that's the input size. Well, let's do an example. I'm just going to draw out an array here. So here's L. I'm going to have 10 positions in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did pretty good. Now remember, each position in the array has an index. 0, 1. And we start counting at 0 here. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is L. I'm going to put some numbers in here as per the assumption here. 2, 9, 12, 19, 20, 22, 29, 43, 48, and 60. So this is my array. Now, every array I'm going to consider is sorted in non-decreasing order like this. Now, you have to be very particular about this, and you got to think about how I formulated the problem initially. So you can think of this as a special case of the problem where I give you an arbitrary array of n integers, and I have to find the key x. So this is a special case of that because I'm only assuming arrays where they're sorted like this. So just keep that in mind. We'll see a better algorithm than the one I'm going to propose. You may have seen it before. But I'm going to be a little bit more particular about things. So I'm just going to erase this. Okay, so before we proceed, imagine if I gave you an instance that looks like this. And I told you that the key was, say, x is, let's go with x is 8. What should my algorithm produce if I gave you an algorithm for this problem? Okay, so if the key is 8, Notice that if I scan across this from left to right, you'll notice that h isn't present in here. So the output should be, of course, -1 because it's not found, right? It's not in there. It's not in L. And hence it's not an X. How about if X was, say, 22? What should it produce? Okay. So let's just start from left to right because that seems kind of natural. So not there, not there, not there, not there, not there. Boom, right there. So I should return back to position 5. So these would be what the solutions would look like, and our algorithm needs to produce these. Okay? So think of the first thing you can use to solve this. So what's the first solution you could think of for doing this? Well, you probably have encountered this in a previous course. The first, most naive thing you can possibly do that will work here is linear search. So, linear search, right? Well, all we have to do is just scan from left to right. Checking the contents at each index of L. Semicolon, if found, if found, i.e. X is found, we should return the location of X. Otherwise, return -1 after recognizing X is not in by scanning all elements in L, right? That's linear search. Very straightforward. So all you do is you just scan from left to right, you check the contents, and if it matches the key, you return the location for which you found it. Simple. In the case where it is not located, you would have to scan from left to right all the way, and after you do this comparison over on the rightmost side, you'll say, hey, look, I couldn't find it. I checked all of them. So you just return -1. So naturally, when you're doing things like this, you need to talk about how you might actually approach doing this. What we're going to do is I'm going to write down some pseudocode for linear search. So I've described the algorithm here, just in words, just to make this a little easier. Then what I'm going to do is I'm going to write out some pseudocode. Now, like I said, the purpose of the pseudocode is to make it so that the algorithm is written clearly enough for you to understand it, but it's not necessarily needing to be written in a particular programming language. So you'll find that I'll adopt Java-like conventions, but you'll find that the way I write down the algorithms is a little bit more formal and less machine-dependent, which that notion of machine dependence will be something I'll talk more about in a later lecture. So here's pseudocode for linear search. So here's my algorithm. So I'm just going to write down what I just said over there. So here's my algorithm. So here's algorithm. I'm going to call it linear search. This is my name. It's going to take an L, the array. It's going to take an M, the length of the array, and X is the key or value. So input, so I gotta always specify what the inputs are for my algorithm. So I have array L of size n value x. Now, you might notice that the way I specified this algorithm, I didn't mention the part about the array being in non-decreasing order. It's because this algorithm works regardless of that assumption. It works on any array L. The reason why I bring this up is that later on, after we talk about some more things, I'm going to show you a better algorithm for this specific problem. So I have to specify the input and the output. So the output is position I such that L sub I, remember this is an index for an array, so I'm getting the element at position I, such that L sub I is equal to X if X is in L, and -1 if X is not in L. Okay. So there's the input output. So you give it a name, you give it input, specify the output. You have to be very clear when you do this. And now I'm going to give the algorithm. So I'm going to start off with a counting variable I'll refer to as I. Then I'm going to have a while loop. So I'm going to go while I is less than n, because remember, the length of the array is n. When I hit position L sub n minus 1, that'll be the last position to check. And, so while I is less than n and L sub I is not equal to x, so I'm going to write down the algorithm and then I'm going to make some remarks. So you know what linear search looks like. I'm just going to go through each one of these until I get a match. And as soon as I get a match, then I'm going to exit the loop. Or if I go all the way through here, I'm going to return saying, hey, look, I defined it. So I'm going to increment I inside my loop. You'll notice that I've implicitly put the check for if it's equal to the key or my value. Up here in the while loop. You can put this easily inside here as an if statement. I want to make it a little bit easier to write down here. So you'd have an if statement in here, then you would have it where, oh, if you get a match, you break out of the loop, but I'm just going to keep things simple. So some things I want to remark once I get finished here. These left arrows, so what I read is the left arrow, that means assignment. So in a programming language, this would be what the equal sign is. However, you'll notice that I use equals in the literal mathematical way. So I use this left arrow. Another symbol that's valid and pretty often used is this one, where you have a colon and then an equal sign. This means define as. You could think of this as well as define as. So this is assignment. Both of these are considered assignment. And keep in mind, I'm not going to be overly particular of how you write down the pseudocode, as long as you're consistent and it's clear to me when I'm reading it. So I have a while loop. So this is written as a while loop where I have a condition. You know how while loops work. So after my while loop, so I'm going to indent that in. Now, keep in mind, I don't need to have that there. I'm just going to have while, and then I'm going to, below my indentation, I'll have if I is equal to n, then return -1. Return -1, else return I. So this is my pseudocode for linear search. So I start off by assigning 0 to I, and then I have this while loop where what I do is each time I increment I, if the key's position, when I put it in here, I check the element's contents. If it doesn't equal x and I is less than n, I just go in. Now, this is what I mean by Java-like syntax. In Java, it assumes shortcutting or short-circuiting. So you may have been taught about short-circuiting in a previous course. Basically, it means when it evaluates this and here, it will evaluate this, whatever appears first, and if this evaluates false, the whole thing won't be checked. So you'll notice the reason why this matters is that when I go through this loop every single time, I keep incrementing until when? It's when I is in fact equal to n, that condition gets violated, right? But if I were checking both these conditions, else sub n, it doesn't exist. Remember, the array can be indexed from 0, 1, 2, 3, all the way up to n minus 1. Not n, though. So I have my while loop. After this finishes, remember, it's going to iterate around, go round, until it violates one of these two conditions. If it gets it where I is equal to n, meaning I scan all the way from left to right, such that n is now going to be equal to I, then I return -1, meaning I didn't find it. Otherwise, I return the position, right? So this is linear search. So I'm going to show to you that linear search is correct. Now, because of the nature of this course and the fact that I can't make certain assumptions about your background, I'm going to prove linear search's correctness directly by making observations about the algorithm itself. Let us prove linear search is correct. Okay. So we got to prove two things, right? We have to do the termination. So first I got to prove that linear search. So my claim is that linear search terminates in finite time. So that's the first claim I need to prove. So that's my first claim. Now, because of this stuff, I need to talk a little bit carefully about how we prove claims. Now, I can't make certain assumptions about your mathematical background other than maybe you've taken one or two university level math courses, possibly more. I know some students that are going to be in here possibly have taken a discrete structures class. If you've taken a class like this, you'll find some of the techniques you've learned in that course to be fairly natural. I'm going to be just using direct methods unless otherwise stated. So I might show you a couple other proof techniques in this course. But we need to mathematically prove that linear search is in fact going to terminate in finite time. So what you need to normally do, and this is what I recommend, because keep in mind that you're going to be writing out some proofs in this class. First, state what you want to prove. And then what you're going to do is, once you've stated this, you've laid out what I call the game plan. You've said, this is what I'm going to prove. And then you're going to follow step after step in statements, chaining them together to reach the ultimate conclusion you're looking for. Now, keep in mind that you'll find very often it's natural to break things into cases. So, for example, here, our algorithm has two possible outcomes, right? Either it returns -1 or it returns I, right? There's going to be two cases. So, I'm going to start off with this case where we terminate in finite time. So, I'm going to say to prove this claim, observe at the beginning of the algorithm variable I is set to value 0. And after each iteration of the while loop, the value of I is increased by 1. The value of I is increased by 1. So before I proceed to the remainder of this, so just notice I start off with 0, and notice that the only thing that happens in this while loop is I just increment I by 1 every single time. So So it's got to invalidate one of these two for this to terminate in finite time, because clearly after that it's either an if or an else, right? Okay. So if the while loop performed an infinite number of iterations, then the value of I would be unbounded. However, this is not possible. Why? Why is it not possible? Why is it not possible? Look over there. So, for this to execute and on and on and on at, like, it never stops, I would have to be unbounded, meaning that I could just keep increasing by 1. But the problem is it doesn't, right? There's a condition there. It says I is less than n. And I is eventually going to have to hit when I is equal to n. So either it's going to end up earlier or it's going to hit that, right? It is not possible as the while loop requires that I is less than n. The while loop will end as soon as I equals n. Now I need a conclusion. Therefore, the algorithm terminates in finite time. Now, normally when you finish writing up a proof, you need to indicate the end of the proof. I usually indicate it with a box. The box indicates the end of the proof. Okay, so this isn't really that bad if you look at it. It's just laying out the argument that dictates this algorithm is going to terminate in finite time. Now, you should not get confused and look at this and say, I'm just listing out some reasons why it terminates. It's not that. What is happening is I'm arguing to you, using a chain of statements, that the argument, in fact, this algorithm has to terminate. That's what you should observe here. So just look at this carefully. I'll give you some more examples. I'll probably give you at least one more at some point. Actually, let's keep this here. I need to still prove the other condition, right? I have to prove that the algorithm actually produces correct output. So let's do that. And I think they'll end this off for the day. So I'm going to do something fun here. Ha! See, I got another board. Okay. Now let's do the second claim. Linear search outputs the correct answer. Linear search outputs the correct answer. That's the claim. So we're going to prove that. Now, I want you to notice that the only places where this is going to output is down here, where we have the return statements. Either it's going to return -1 or it's going to return I. Let's observe this, and we're going to find out we're going to have two cases. The final line the final line of the algorithm returns value I. This is correct as the while loop, ended, and what? And I is less than n. I want you to, the big thing I want you to observe here is that we have an if and an else here. So the while loop terminates, and then you have two choices. Either I is equal to n, or it's otherwise. Well, you know that I is in fact going to only be less than n otherwise if it's not equal to n, right? Well, what does that mean? That means it's some number between 0 and n minus 1 inclusively. So that means what? Which implies that else of I is equal to x. So that's the first case, where x is in L. We need the second case now. Now we must show that the algorithm returns, let's get a little close to the right side, returns value -1 if and only if the value x is not in L. Now, for those that aren't familiar with the phrase if and only if, all you need to look at this as is the part saying that the algorithm returns -1 is interchangeable with the statement, at least logically, that the value x is not in L. So if I can show this is equivalent to that, we're done. Okay, I'm just going to switch markers here. We're going to use the last few minutes just to wrap things up, okay? Okay, here we go. When the algorithm, this marker's even worse. We quickly switch that one again. Let's switch that one with this one. When the algorithm begins its set, and I apologize for the train if you can hear a train. I know it's telling me time is up almost for us today. It sets I to value 0. And then I is increased by 1 in each iteration of the while loop, right? That's what we said before. Each iteration of the while loop. For I to be increased in an iteration of the loop, it must be what? There's two things you need to observe here. For this loop to continue executing each iteration, it must be that both of these are satisfied, right? That's going to be a main observation here. So for I to be increased in an iteration of the loop, it must be that when it must be at, let's go, it must be at that time that both, I'm just going to finish it up over here. That both I is less than n, and L sub I not equal to x are true, because it's plural. Are true. This means that the algorithm compares the value x against each value in L, right? Because remember, it scans from left to right, and each time it had to have been that both of these were satisfied, right? Because remember, we know it terminates. So it means that we had to go through each one of these and it said, hey look, both of those conditions are true, so we're going to keep going and increasing I. So this means that the algorithm compares the value x against each value in L if at the end of the while loop, the condition I is less than n is false. What does that mean? If it fails that this is no longer true anymore, that means I is equal to n, right? This means I is equal to n. And the algorithm has checked all values in L, and none of them equal x. And none of them equal x. Hence, here's my conclusion. Hence, the return value -1 is correct. Now, technically, I would have an overbroadening concluding statement saying, therefore, linear search is correct. But you'll find that in this class, I'm not going to be crazy formal with things. But still, remember, this is not just me listing out reasons why it's correct. It is that I'm making an argument. So what I do is I look at the algorithm and I observe properties of the algorithm. And from there, I pull out justifications. So in this case, I broke it into two cases. One for which the return value was I, and the second case where the return value was -1. And I looked at what happened in each one of these situations. So I read out what the algorithm does, and I observed what should come out of it. So it'll almost look like I'm writing out what the algorithm does, but I observe special properties it might have. That being said, this proof technique you'll find that for simple algorithms is fine, but for more complicated algorithms it can be an absolute nightmare. So in this course we'll find that this technique will work fine for us, but in a third year class you might find some more techniques that are helpful. I'll be showing you a couple other tricks in the hat to make things easier as well as we progress. So I think this is the perfect place for me to stop actually. Next time, what we're going to do is we're going to start talking about analysis of algorithms. So we'll talk about what it means to, what are some beneficial metrics for which we can talk about an algorithm. So like what are things that are ideal for an algorithm for solving a problem? And how can we analyze an algorithm? So I'll start talking about that next time. So thank you much for watching and have yourself a beautiful day. I'll see you later.